Purpose of this video is to use photoelectron spectroscopy to review some of the concepts of effective nuclear charge and shielding. So I'm going to review just a little bit here by way of this Bohr model that I have drawn, what shielding is and how it is a factor in terms of periodicity, and also what effective nuclear charge is and how that affects things such as ionization energy and atomic radii. So what I have drawn here, this is a Bohr model for silicon, and if we were to talk about the size of silicon in comparison to something like carbon, carbon's only going to have 2 principal energy levels as opposed to 3. So carbon is going to be smaller because there's less layers, and we say there's less shielding. Now what shielding is the fact that the force on these electrons out here in the outermost shell is a little bit less, because as we have this nuclear charge, higher number of protons, it draws these closer electrons in even more, which then in return reduces the force on the outer ones. So it allows those further electrons from the nucleus in the 3rd principal energy level, they're going to be further away, whereas in carbon there's only 2 layers, there's less shielding. Now that one's fairly simple. If I would compare this silicon to phosphorus, we're going to have 15 protons, and we're going to have an additional electron in phosphorus. So we're not adding any more layers, so there's really no additional shielding. But what we find is that the phosphorus atom is actually slightly smaller because of the additional nuclear charge. So we would say phosphorus, silicon and phosphorus have the same shielding. However, phosphorus is smaller due to a more effective nuclear charge, or a greater nuclear charge. Also, going back and doing the same comparison, if I compare the ionization energy required to remove an electron from an atom in the gas phase, for carbon, it's going to be a higher ionization energy for carbon than it is for silicon. Because for carbon there's less shielding, the electrons are drawn in with a greater force, part of Coulomb's law, it's an inverse square law, so it's exponentially higher. And because of that, we find that there is a higher ionization energy in carbon than there is in silicon. Now if I compare my silicon to phosphorus, remember when I added that additional electron and also had added the additional proton, we said that the nuclear charge draws those in tighter. So that means in general that it's going to take a greater amount of energy to remove an electron from phosphorus than it is from silicon. And there's plenty of comparisons, and there's also some anomalies to those that we encounter, and things that as you study more and more chemistry that don't follow the periodic trend exactly. But for the most part, what we find is on a periodic table as we go up and to the right, that the atomic radius is smaller, and therefore the ionization energy increases. Now again, the reasoning behind that is as we go up we get less shielding, and then within a row as we go to the right we get a more effective nuclear charge. So when we're trying to explain those, we don't say because of where it is on the periodic table that makes it smaller or that makes its ionization energy greater. We say, depending on the type of comparison, is it because of a different amount of shielding up and down, or is it because of effective nuclear charge as we go from left to right? And you can definitely, as you study these in opposite, you will find some anomalies where maybe the effective nuclear charge becomes more significant than the shielding, but again, for the most part, we're looking up and down. Is it shielding? Left and right? If not, then is it effective nuclear charge? And I'm not going to spend a lot of time on this video talking about the anomalies. The next thing I want to talk about is successive ionization energy, which is not what we're going to do in photoelectron spectroscopy, but I don't want you to confuse PES with successive ionization energy. Successive ionization energy is if we go in here and we remove this electron, it's going to take some energy. When we go back to remove another electron, now we've only got 13 negatives with 14 positives, so due to the greater nuclear charge, it's going to take even more energy to remove the next one. And then even an increased amount of energy as we remove the 3rd, and even more when we remove the 4th. So we see this steady increase in the amount of energy. However, once we've removed those 4 electrons, if we successively go ahead and remove a 5th electron, now we find that we get this really, really large increase in the amount of ionization energy. The reason for that, we've not only changed the positive proton to negative electron ratio, but at the point once we've taken away those 4, In the outermost principal energy level, now we see this jump because there's less shielding on this electron that's in that lower principal energy level, and therefore it requires more energy to remove it. Now if we continued on and we removed 6 and 7 and 8 and so on and so forth, we would still see kind of a somewhat steady increase, and we wouldn't see the big jump until we have removed that whole second layer, and then we start removing electrons from the first principal energy level. Photoelectron spectroscopy is not successive ionization energy. It is a type of ionization energy where we're bombarding atoms with enough energy to essentially cause all of the electrons to move, to quantum leap, to undergo some sort of a change. And again, you can picture it, rather than taking one, then another, here we're just bombarding it and we're studying all of them simultaneously at one time. So we're analyzing the energies, plural, for all of the electrons, and that's when we end up with what's known as a photoelectron spectrum, which is what we have here. And this is the photoelectron spectrum of nitrogen, which I've drawn the Bohr model down below so I can talk about some of the basics of PES. But again, the first thing is it's not successive. It is all the ionization energies at one time, analyzed, plotted on a graph for us to analyze and study. First thing I want to point out is that you need to look at the axis on the graph, the x-axis on the graph, because it's not uncommon to see these in what we would say kind of reverse graphing order from high to low. However, I'll show you some here in a moment where it actually goes from low to high. So you need to look at that and determine which way it is we're reading this graph. The next thing has to do with the peak heights. The peak heights tell us the number of electrons. So we need to understand a little bit about electron configuration in order to analyze PES data. And I'll go through and I'll show you those as we go through here, but this represents 2 electrons. This is 2 electrons, and again I'll show you how we know that in a moment, because this one represents 2, then this one here, this is going to represent 3 electrons. So we get a total here of 7 electrons, which is how I know this is nitrogen. Now, how do I know this from a standpoint of the electron configuration? Well, these are my highest energy electrons. Those are the ones that are closest to the nucleus. So we say these are the 1s2 level electrons. These are the first principal energy level, the 1s sublevel electrons, and they have the highest energy. And we'll talk more why the higher energy, but as I move on out a little bit lower energy, now we have the 2s2 electrons, and lastly we have the 2p3 electrons. So that matches the electron configuration, and the easy way to do that when you're doing PES is to find your highest energy side of the axis, depending on which way it's oriented, and then just start counting with electron configuration according to the off-ball principle. Label 1s2 and just proceed right on through there. And that's definitely something you need to be able to do, and then that helps with explaining some of the other things that we will encounter. Now, I'm not going to talk about the differences in these 2 peaks right at this point, but I will go back and explain those later. We're going to talk about them collectively. So from a standpoint of just collectively, we see that these electrons here, these 2 electrons, require relatively high energy to remove because they're closest to the nucleus. There's nothing underlying, so there's no shielding effect, and right beside the 2 electrons we've got 7 protons, so we have a very effective nuclear charge within the atom itself, which is drawing those first 2 electrons in. So the binding energy, or the ionization energy, to remove those is relatively high. On the other hand, if you take a look, and again this scale is not counting in linear fashion, 100, 10, 1, 0.1, now we see that we've got this relatively low, when compared to the other energy, relatively low energy here to remove these other 5 electrons, the 5 valence electrons. The reason for that, those 5 electrons are shielded by the underlying electrons. The highly effective nuclear charge pulls these first 2 electrons in, therefore making it less energy to remove the valence electrons. So the next photoelectron spectrum that I have here, I've not labeled what it is yet, and it's not uncommon to see these peak heights actually labeled for you on these. That's what that represents, is the relative number of electrons, or the peak heights. But even if those weren't labeled, using some of the things I've talked about already, we need to go and we need to find where our high energy is. Now this one's a little bit different because we've got a split graph, and it's actually got our energy, high energy, over here on the right. So this is what we would say maybe normal x-axis numbers, but it is split. We've got 0 to 10 on one graph and then 10 to 100 on the next. So it's a little bit different than the graph that we looked at a moment ago. Locating the highest energy and then working your way to the lower energy by way of electron configuration is probably the easiest way to understand and interpret what's taking place on a photoelectron spectrum. So again, those first electrons, these will be 1s2, and then we'll have 2s2, and here we have 2p4. So this has 8 total electrons, so this would be the photoelectron spectrum of oxygen. Again, notice high energy here, 52.6 for the closest electrons to the nucleus, whereas our second principal energy electrons between 1.3 and 3. And again, I'm still looking at those collectively. We'll differentiate between those two numbers in a moment.